Hello, ladies and gentlemen. Welcome to another episode of Aerospace Engineering with Brian McNulty. Today, we're just going to have a conversation that is going to be an extension of our discussion of the last episode. I didn't get through all the forces, and I'm not going to go through the electric force in this one because we'll learn more about all that in the electricity and magnetism series that I'll be doing later. But one that I didn't mention was tension, and it's something that's given rise to a lot in physics in our everyday world, and so I figure it was worth doing a video on that, and so let's do a problem right now. Before we get started, I think it's worth reviewing a little bit from some of the concepts about centripetal motion that I introduced in the last episode. So remember, the centripetal force is actually not a new type of force that it's not a new type of force. What it is, it's just a type of force that we already know about. It could be the gravitational force, it could be the frictional force, it could be the normal force, it could be the electric force, it could even be tension. And so, like I said, we're going to take a look at an example of this where the centripetal force, the force responsible for keeping an object in a circle, is going to be the tension force. Alright, so you can imagine a tabletop here, and here are the legs. And you can imagine nailing a stake or a nail or something into the center of this table. And basically what that's going to serve as is the center point of the circular motion of this ball that is tethered to it by this rope here. Alright? So the types of forces that are acting on this ball right now, you can imagine the circle that it's going to travel around here is going to be something like this. So that's going to be its path. And we know about, the gravitational force that acts on objects. And we know that since it's sitting on a table and it's not succumbing to the gravitational force, it's at what's called mechanical equilibrium. And so we introduce this normal force, the force normal to the surface of the table, to balance that out. Now, one thing that we're not accounting for is the forces in the horizontal direction, or the centripetal force. In other words, the force that is acting radial inward on this object to keep it in this circular path. And so I'm going to draw that in right now, and we're just going to call that the centripetal force for now. Now that we know that the vertical components, the gravitational force and the normal force, are going to cancel each other out, we don't need to bother with those. Those aren't going to have any part in the object's circular motion. But what will? You guessed it, the centripetal force. And in this case, since the object is tied to a rope that is responsible for keeping this object in a circular motion, we are going to use the tension force. And the tension force is present in the rope, and it points radial inward. Let's check out the force diagram from an aerial view to see what I mean. So here is the aerial view of the diagram to the right. And you see I've given you the velocity, I've given you the mass of the ball, and I've given you the length of the string. And we already said that the only force acting on this object is going to be the tension force. So the centripetal force is just equal to the tension force, which is also going to be the net force, because it's the only force there. And so we can move on to Newton's second law, and we can recall that F is equal to m times A. Well, we said in the previous video that A, when we're talking about circular motion, is going to be v squared divided by r. That turns net force, which is tension, into m times v squared divided by r. Now, since we know the all those values, I mean, we can just plug them in now. And so we have the mass of the ball, which is going to be 2 kilograms. And then we have the velocity, which is going to be 4 meters per second. Don't forget to square that. And then the radius of the circle is just going to be the length of that rope, which is 5 meters. And so when we do that, we come out to get 32 over 5, which is going to be 6.4 newtons, because we're measuring force here. And so that is going to be the tension in the rope. Next, we're going to take a look at a dirt bike rider as he goes through a loop. You see this on things like extreme sports channels and other events like that, and so I thought it would be an interesting problem to do. And so without waiting around, let's just get started on it. As with all of these problems, we have to draw a force diagram first, and as you can see, I've given the mass of the rider and the bike together. I've also shown the radius of the loop that he's going around, and I've given the velocity as 25 meters per second. You can also see that I've drawn the forces here. Now, you might be confused because the normal force in any of the other problems that we've been doing has typically been in the opposite direction of gravity. But in centripetal motion, it's different. The normal force actually is normal to the surface, and the surface is pushing on the rider. So the normal force, always being a push force, falls in the same direction as the gravitational force, which is inward radially, as is the acceleration. Alright, so the question is, what is the normal force on the motorcyclist, given all these parameters? So to first figure out, well, we already drew the force diagram. That's always going to be the first step. The second step is going to be just apply Isaac Newton's second law. So F equals ma. That means that the acceleration is equal to the net force divided by m. All right, so now we got to figure out what the net force is. What is that? Okay, well, we can look at the force diagram again, and we can see that the normal force and the gravitational force are both pointed inward. And they're both pointed in the same direction, moreover. And since they are pointed inward radially, that means that they are both positive. And so, rearranging this, I'm also going to just do this all in one step here. We did say this multiple times already. A equals the square of the speed over the radius of the circle. So that means that v squared over r is going to be equal to the net force, which is the force of gravity given by mass times gravitational acceleration. We said they're both positive, so this is positive, and then we're also, since the normal force is going to be in the same direction, we are going to put the normal force here. And then we are going to divide by the mass. So what we have when we solve for the normal force is going to be, we're going to multiply both sides out by m. So I'm going to rewrite this one step at a time here. We multiplied the m out, and we just get mg plus the normal force. Now, if we subtract mg from both sides, that's going to give us the normal force is equal to mv squared divided by r minus mg. Let's plug in some values. We were given that the mass of the rider and the bike together are 250 kilograms, and we multiply that by the velocity, which was given to be 25 meters per second. Don't forget to square that, by the way. And then we divide by the radius of the circle, which I said was 20 meters. And so let's do that. And then don't forget to subtract the gravitational force, which is going to be the mass times g, little g, which is 9.8 meters per second squared. And there's your equation for the normal force. Let's say you wanted to solve for the minimum velocity that would be required for that same motorcyclist to complete that loop without falling off of the top of the loop and crashing inevitably. And so essentially what you do for that is you just set the normal force equal to 0. And if the normal force is anything less than 0, the rider will fall. If the normal force is exactly 0, the rider will feel weightless against the surface of the loop. Let's just use our last equation and plug in 0 for the normal force, and then we'll solve for velocity to get the minimum speed at which that motorcyclist can travel before he does not make it through one entire rotation of that loop. So here's the problem statement. What is the minimum velocity the rider must have to complete the loop without falling off? And you see our velocity is no longer 25 meters per second. That's what we're going to solve for. But what I just said is we set the normal force equal to 0. So we go through this whole process again, and instead of the sum of the forces being both the normal force and gravity, like I said, the normal force goes to 0, and that means that this goes to 0, and also means that this goes to 0. Now we're left with this equation that looks like this. 0 equals mv squared over r minus mg. Alright, so we're going to solve for velocity here. Now, by adding mg to both sides, just performing our basic algebra, we're going to get mg is equal to the centripetal acceleration divided by r. Do more algebra, and we're going to end up with, let's see, rmg divided by m, and then since the velocity is squared, we're going to take the square root of that, and that's going to give us our velocity. Notice these m's just cancel out, and you end up with the equation velocity for him to barely make it through the loop is going to be equal to the square root of the product of the radius and the gravitational acceleration. After we plug in those values into the calculator, we get a velocity solution of 14 meters per second. That's the minimum speed that he has to be traveling before he successfully does the loop. Okay, so that all makes sense. That means that because the normal force is the force of the surface of the loop, the interior surface of the loop, pushing on the rider and keeping him on track, you have to have at least it has to be greater than or equal to 0. If it's less than that, he has no hope of making it through the circle. So in this video, we did an example using tension force, which we did not cover in the previous one, and then we flipped our circular motion to a vertical circle, which changed the whole problem. It changed the types of forces that we're dealing with. We're now introducing gravity and the normal force into these vertical circular motion problems. And so that's going to be it for today. I hope you guys enjoyed the video. Please like and subscribe if this helped you out. Let me know in the comments. And I'll see you guys on the next episode of Aerospace Engineering with Brian McNulty. Thanks for viewing.